next up, we're going to have Emma Wingreen from code.org. She's a curriculum writer coming up. As I mentioned, this afternoon is going to be focused more on curriculum, and in particular, we want to look at how people are doing curriculum for teaching software engineering, teaching coding, teaching computational thinking with block-based coding. And we want to look at kind of the best practices in this area because it's something that's been growing over the last decade. There's enough experience out there to really say these are better and worse things to do. And so we asked some of the people to come in and actually tell us all about that.
Hi, everyone. Thank you. I'm excited to kick off this afternoon of curriculum development. My name is Emma Wingreen. I am a curriculum writer at code.org. I put this presentation together with the help of Amy Berkut-Woodman, who is a curriculum development manager, and Mike Harvey on our engineering team. Today I'm going to talk about a couple different code.org student labs that we use, explain how we build on existing labs using helper libraries and block pools, explain what those even mean, and do a demo of one of our upcoming CS Connections modules called Simulating a Marine Ecosystem. So what exactly are student project labs? Here's an example of Game Lab. This is the Game Lab interface. It's designed for middle school students, and though it looks like Blockly, it's not actually. So it's using a technology called Droplet, which adds a block-like interface and allows students to morph between blocks mode and text mode. So notice how when you change between blocks and text, what's actually on screen isn't changing, it's just the formatting. So students have the option to write their code in JavaScript, or they can drag out blocks from the toolbox. It looks a little bit more complex than some of the labs I'll show in a minute for elementary schoolers, and that's because, as I said, it was designed for this middle school audience. And you can see that there's a fairly extensive toolbox as well. Game Lab, similar to Sprite Lab and Poetry Lab, all use P5 Play, which is a game engine built on P5.js. And you can see there's 3 lines of code here. So this first line is creating a sprite at the center of the screen. Second, we're giving that sprite an animation. So in this case, the crab image. And third, we draw the sprite to the screen. So if a student actually wanted to animate this sprite, they would need to add in a draw loop and understand how that works. Comparing Game Lab now to Sprite Lab, we wanted something more user-friendly for elementary school students, which led to the creation of Sprite Lab. You can see that the blocks are simplified, the toolbox is less extensive. Something that I want to point out here is that this is a particular level of one of our modules. We actually have the ability to customize each toolbox, so we can choose which blocks students are seeing on any given level. Game Lab has a higher ceiling than Sprite Lab, but also a higher floor. So many students start out using Sprite Lab before moving on to Game Lab. This is, in the play space, it looks very similar to Game Lab, but there's actually only one block here that's doing what 3 blocks did in Game Lab. Students also have the ability to see their code written out in JavaScript, but when they're programming, they're using Blockly rather than being able to type in JavaScript. From Sprite Lab, we created different child labs. So this is Poetry Lab, which inherits everything from Sprite Lab. What's unique about Poetry Lab is that it has its own separate user interface. So you can see this poem selector drop-down menu, and there's an extensive library for handling custom poem animations to be able to bring this poem to life. The Select Poem drop-down menu controls the text that's animated at runtime, which saves the student from having to add in print blocks. So before, for every line of code that students wanted to appear on screen, they would have to add in a new print block, type each line of their poem. Here, they can choose from some built-in poems, and they can easily enter their own just by typing it into the Enter Your Own user face. Since creating Poetry Lab, we realized that there was a large startup cost, which was having engineers have to create this user interface for us and the underlying library. So we thought maybe there's an easier way that we can do this. Maybe we can just build on existing labs that we have in order to create our new CS Connections modules. So that's where we get helper libraries and block pools. What do I mean exactly by that? So this is an example of our simulating marine ecosystems level. You can see that there's actually only one block in the starter code, and it kind of has nothing to do with what's happening on screen. It's an event block that says when the fish touches the algae, but we haven't actually told it to do anything. So instead of having students add all of the code to create this underwater scene, we put all of that into a helper library, and it creates sort of a magic experience for students where they don't have to see very complex starter code, they don't have to build out any code in order to get their program up and running. So there's also no risk of students accidentally deleting these start blocks. Something that we saw in student observations was that if students entered into a new level, saw a lot of starter code that was supposed to help them complete their program, and they didn't understand what it did, they would just drag it back and delete it, back into the toolbox and delete it. So we didn't want to have that happen, so we hid it all into this helper library. This is an example of what that ocean setup looks like in the helper library. You can see that there were initially a lot of blocks that we would have to have students add. They're adding in the boat, giving it a behavior, adding in several different fish, adding in algae. You can also notice that after a certain number of seconds, more algae is added. So we figured instead of having to teach students how to do all of that, we would just kind of hide it behind the scenes with no extra UI. As we're prototyping these new CS Connections modules, we'll occasionally discover that we need new blocks. In some cases, like our marine ecosystems module, these are really context specific. So we want to create, for example, a block that will model a fish eating an algae sprite. That's not super generalizable. We don't necessarily want that to show up across all of our Sprite Lab toolboxes. So we'll use something called block pools to create a set of blocks that's used just for these specific modules, or maybe just for prototyping new levels. Each block has a JSON configuration that the curriculum team owns, as well as a helper function that is giving it something to do kind of behind the scenes. So like the helper libraries, these functions expand the capabilities of Sprite Lab and determine what the blocks actually do. So what does that look like? These are the examples of two of the new blocks that we added for our ecosystems module. So we have our catch and eat block, and they're actually the same as an existing block, which is this remove block. So I'll go back, and you can see that the configuration and the function are the same. The only thing that's changing is the name. So actually, the catch and eat blocks do the same thing as each other, but we figured that it makes more sense for students to connect a catch block to the boat catches the fish, and the fish eats the algae. Here's an example of another custom block that we made for our ecosystems module. This one was a little bit more complex. So this is an example of a conditional statement that uses language that would be more familiar to an elementary school student. So if there's too much, in this case, it defaulted to the image of the bear, but it would be if there's too much algae, if there's too little, if there's just the right amount. Rather than having students have to program in a complex inequality, kind of choosing arbitrary numbers for how much constitutes too much algae, we just said 19, and how much is too little, we kind of chose 2 because that appears on screen. So we abstracted that into a block that would make more sense for students. What does this all look like in practice? So here is what students are working towards as they complete this series of levels. So you can see this is the final level in this particular lesson, and it has all of these custom blocks and the helper library ocean setup before students even program. So you can see that students are adding in these custom blocks to catch an object, eat an object, and they're adding in a block inside of each conditional. So something's happening if there's too much algae, which is that the coral dies. You can see it change color to this like faded kind of pink color. If there's too little, you would see all the fish leave the screen. And if there's just the right amount, the coral heals. Okay, that's it. Thank you to everyone who helped me put together this presentation. And thank you to all of the former Code.org employees, including Josh Caldwell, for paving the way for block pools and helper libraries.
Thank you, Emma. Any questions in the room? Make your way to a mic if so, while I check the live stream. Let's see. Looks like Christopher might have a question.
Yeah, so I was going to start with a comment, which is I think that instinct to delete code you don't understand is something which almost every software engineer continues to carry with them throughout their career. So it's good to know it's in there from the very beginning. I was curious. I didn't quite follow the distinction be like what goes in the helper libraries and what goes in the block pools. Is it just block stuff in the block pools and everything else is in the helper libraries?
Yeah, so I should have prefaced this with saying this is kind of taking you all to the outer limits of my technical knowledge of this, but I can try and answer. So the helper libraries have some functionality, and a lot of what we would want the helper libraries to do is to set up the environment. So it's showing something on screen before students are even adding in any code. So kind of like what the starter code would be doing. And block pools we would create for blocks that we want students to see. So those catch and eat blocks or the conditional statement, those would show up in the toolbox and students would actually be able to and would be expected to drag them from the toolbox and add them to their code. Does that answer your question? Okay.
Absolutely.
Great. We have a question on the chat, which is, how is a new curriculum evaluated before deployment? For example, are potential learning gains with students measured?
I can see if I can answer that. Evaluated in terms of for content knowledge or for?
Like potential learning gains, are those measured with students? I think they're trying to get at just like, I guess, how do you know when your curriculum is good to go and ready to be used with students?
Yeah. I can speak a little to this now and also give a plug for the curriculum developer panel at 4 Eastern time.
Yeah.
But something that's really important to us is piloting all of our modules. So this ecosystems module that I was talking about today, when it's going to be launched this summer, we've actually already piloted it last fall. So we released a version of it, we released a beta version, and then we piloted it with certain teachers. But that's a great question. I think we start from a place of looking at the content standards, so looking at the science standards specifically, and then trying to figure out how we can incorporate computer science standards as well. So there's kind of this twofold approach of, are we meeting the science standards and are we meeting the computer science standards? And I think that the best way that we get that feedback is from teachers directly, like did this land when they were teaching it with their students?
Gotcha. Awesome. Let's see. And do you have another question?
Yeah.
Okay, go for it, Christopher.
So I'm curious to know the decision-making process that goes that you go through when you're thinking about the process of maybe replacing a bunch of primitive blocks with a more composite block, or perhaps the opposite. How much of that is driven by experience, like seeing how the kids are using it? How much of it is based on sort of more theoretical principles?
Yeah, so I can speak to specifically the conditional block that I talked to about just now. That came from feedback from teachers saying, you know, we tried your lessons, we really liked it, but students really got stuck on this. They don't, maybe they haven't learned inequalities, maybe that's like a math standard that's beyond the grade level for them. Or maybe it's just a concept that could resonate with students, but in a more simplified context. So I don't know if you saw on screen, but we were referring to that block as the Goldilocks block, because we figured that that was a context that students would understand of like too much something, too little, or just the right amount, without having to be super technical about figuring out the exact number. So I'd say part of it is just kind of knowing our student audience, and then also sometimes we'll release something and depending on feedback realize, okay, maybe we have to revise this block, simplify it. Maybe students don't need to be learning conditionals in this particular unit at all, and we could make that decision as well.
Great, thanks.
Awesome. I don't see any other questions on the chat, so Thank you, Emma, and we can pass it back to Rachel.